to our next talk and our Tobin track. We have filled up this room because everyone wants to know about the invisible ink of compression, right? You're in the right place, right? I want to introduce you to Logic. He will give us this awesome presentation today about this cool topic. And the only thing he wanted me to tell you is that he's not a security researcher.
Streams in here. If we interpret it as a TCP stream, so, well, actually we'll get to that in a second, but as an HTTP stream, they are identical. You'll see two different colors of arrows. Green is the normal one, red is the suspicious one, because red's suspicious. And if we look at it in the context of a TCP stream, in this case, it's a little bit different under the hood. So it might be an eye chart here, but the top we can see the deflate. There's the garbage there, and the deflate there. It's just a little bit more garbage. That's the takeaway. And we're gonna. I lied on the program. This is technical, but narratively speaking, this is the foreshadowing. We'll peel it back and explain this all. So this is going to be a little. But what I highlighted there in hex, that's the binary of the actual compressed data. In CyberChef, if anybody's familiar with it, it's just kind of a good Swiss Army knife for encoding and decoding things. We throw it in there with a recipe of from hex to make it binary, and then we inflate it with the deflate algorithm. And in this case, we can see the HTML that it's supposed to decompress to, which is, the tags, and then the body of it, or the actual text of it is nothing unusual here. But yeah, we'll go back and take a look at the suspicious one. This one, there's a lot more binary to highlight. We take it into CyberChef, and it's the same thing. And that's kind of the thing to keep in the back of your head for the rest of this. And to get super technical, there's this really cool tool that allows you to pop the hood and look at the internals of deflate. It's called ImpGen. We'll get a lot more into it. I'm just kind of giving a brief preview, foreshadowing. This is kind of just like all the tokens or characters it's building up. And you can see the matches, the pattern matches. You can look at the tables of all the symbols and all that. But this is just kind of what normal looks like. This is the table of the characters it actually uses, no less, no more. But if we look at the suspicious one, already there's a lot more stuff in here. Yellow is the table, blue is the actual data. For the first block of data, you see the building up of HTML, but then it ends the block. Yet for the actual table of symbols, it has way more symbols than it's actually using. That's suspicious. And then on the next block, it's just the letter B, and it ends that block. Yeah. And, there's also a tool that I'll be talking about, just released a few days ago, that allows you to detect suspicious things in deflate. So it's definitely telling me about all this Huffman table stuff. It could even, it even has the ability to scrape the data out of there if there's data hidden in there. In this case, the hidden data in that one was, but actually there's something incredibly unusual here. So that was network proof of concept. Mostly it's doing some Huffman table manipulation. So it's the Huffman ignorance of some more general ignorance of different things you can do. And that's just a small part of what we're going to get into. So that's kind of the preview. So deflate. If nobody's heard of it before, which if you're into compression, that'd be weird. But if you're not into compression, that's cool. Either am I. This talk's not about compression. So it's really common. It's in Gzip. It's HTTP, PNG, and a lot of other things. It's a really, really common, just general purpose compression algorithm. And actually, it's kind of two algorithms. It's LZ77-ish, because patents or something. I don't know. And then the Huffman codes. And we'll get into both of those. But fortunately, it's actually really straightforward, I think. It's not really super mathy. It's conceptually pretty easy to understand. And this slide right here kind of has nothing to do with the deck. I think it's just kind of something, just a hackery thing to keep in mind when you approach systems. I think a lot of people that are hackers kind of already know this. The difference between what a system's intended to do and what it actually does. And you'll be more effective if you can just throw away that first part, what a system actually does. If you think about what a system actually does, that's going to get in your way of progress. What the system does, compresses data, decompresses data. That's not what I'm doing. What it actually does, it does these words here, that whatever. So let's talk about that first algorithm, the LZ77. That's like the pattern matching. So if you have a bunch of text and then you come into text that well, I saw this word before, I saw this phrase before, you can, with numbers, you can say, well, that pattern that I saw before, it was 10 bytes. And I go back 23 bytes to find it. So that's just two numbers as opposed to a long string of text. It's just a shorthand. That's really all it is conceptually. I know this is small. I'll read this, but as a proof of concept, conceptually, we have the phrase, the hacker was hacking the hack system using hacking scripts written by other hackers who had hacked it before. Yeah, it's a terrible sentence, but there's a lot of repetition, so that's why I went with that. So, as we're building up the sentence, we can say the hacker was, and I'll zoom in here. So we start with the hacker was, but the next word is hacking, so we saw that word before. And we're going to say 5 characters, not 4 for hack, because there was a space before hacker, so we're cannibalizing that as well. So that linked distance pair is just 5, and then go back 11 to find it. That's it. That's all the LZ77 really is. And as we go, there's a lot of content. You just trust me, that's how the whole thing works. Those are all the linked distance pairs. That's what that would look like. And in just plain ASCII without compression, 112 bytes would be that sentence. But just using LZ and not the Huffman tables, that brings it down to 81 bytes. So now, and I'm going to be in and out of this slide a lot. These are just kind of the tools. I kind of organized it this way to when I talk about a tool, I kind of come back to this slide so you kind of have a conceptual idea of not just looking at a bunch of screenshots or videos. But CyberChef, I kind of already explained. That's for encoding, decoding. We'll use that a lot. InfGen is the tool to pop the hood of the compression to look on what's inside. DEFLATE is a tool that I wrote to start under the hood and create compression manually. And then I'm using a fork of InfGen because mine spits out the whole binary blob in color-coded with all the fields. So yeah, let's breathe manually for a second here with DEFLATE, just to kind of prove the example, the conceptual example. We'll get our hands dirty with it. So in this case, we're just going to be building up that phrase, character by character. We got the hacker in this case, and then a space, was, and then we're going to say 511. We can manually put in the link distance pair, and then ing, and then end the block. And then it spits out this ASCII hex. That's our binary blob. So to prove that that was doing what we expected to do, we go into CyberChef, and we pop that ASCII hex in there. And we're going to do from hex to make it a binary blob, so then we can inflate it with the deflate algorithm. In this case, we get the hacker was hacking. So it works. And then just to show InfGen, just to show it, we can put in that binary blob. We just echo it out, and we pipe it to XXD -R-P to make it binary, and then we pipe it to InfGen, and then we can see every single field under the hood, but also I'm highlighting that 511. It has all the characters down the line, but then we see 5 characters, go back 11 to find it, so that works. I'm going to do the same exact exercise again, but to kind of revisit that ambiguity concept. So we're going to do the same phrase, the hacker was hacking. So build that up. But this time we're doing 411. So we're not cannibalizing that space. We're just saying, just take the word hack. We end up with that binary blob, and we come back to CyberChef. We have our from hex, and then we inflate it. Hacker was hacking. Whole point of that is, that sounds pretty obvious, but the ambiguity is what's important. There's more than one way to do it. It's not a one-to-one relationship, and I love that when that happens. And then in InfGen, just for illustration purposes, just to validate, you pop the hood, and what we're just looking for here is to see that 411. So yeah, down there we have the 411. All right, so let's get ignorant with LZ77 specifically, these linked distance things. There's 2 different things we can do and be ignorant with this. There's illegal lengths, like bad lengths, and also we have distances, so illegal distances. I quoted illegal for the links because, so we have the letters HA in our buffer, and then what we're saying with this linked distance pair is we're going to have 7 more characters, go back 2 to find it. So going back 2, we have the HA, but 7 characters, what does that mean? This is a feature, not a bug. And instead of saying what it is actually supposed to do, we have the tools. Let's just do it and see what happens, right? So we're putting in HA72, and we get our binary blob. Pump it into CyberChef, see what CyberChef thinks about it. And we get a lot of laughter. Yeah, that. And in this case, it ends with an H. So that's another side effect. I chose an even number for the length just to illustrate that it loops, and if it's an odd number, it just ends at whatever it was at. So that's not really that ignorant. That's what it's supposed to do. This, on the other hand, we're going to go into this for at least 10 minutes. This one is wild. There's a lot of different directions this will take us. So in this case, we have, again, the same HA. We're going to say 7 characters, which that's fine, but go back 20 in the buffer. Where's that? And you know, when you're using gzip or something like that, it's never going to create those linked distance pairs. But like, again, we have the tools. We can put that in there under the hood. Let's do it and see what actually happens. So we're putting in the HA. In this case, it did 742. You know, and we get our little buffer here. Let's see what CyberChef thinks. And this is what CyberChef thinks. This isn't what all implementations think. Like gzip might be a little bit different, but we're just seeing what this thinks. So we're going to do back 2 hex just because it's going to be unprintable stuff. And in this case, we have this 6861, which is the HA, and then a bunch of nulls. Yeah, where'd those nulls come from? We're going to get down. We're going to get to the bottom of that towards the end of all this ignorance, and it's not as interesting as I wanted. I mean, of course, heartbleed for compression, that'd be great. No. Well, that wouldn't be great. But yeah, and then to look under the hood to see what InfGen thinks, it actually does throw the warning. Looking at the 42.2, it says that's a distance too far back, and yeah, it is. So instead of like looking at gzip or something super complicated, I wanted to see, well, CyberChef did this, where is it getting its nulls? I kind of looked at their source code. I didn't come to the answer right away, but I saw something really, really interesting. And this is if you know CyberChef, the authors, it's GCHQ, the British NSA, which is just, that's not relevant. It's just funny to me. So they put in this comment here: raw inflate sometimes messes up and returns nonsense like this. And you know, like the square brackets and dots, that's the nonsense that that 4 bytes of hex below that produced when they try to inflate it. So they didn't understand it. They just built an edge case around this to error on it. And like in shorthand, it's if it finds a payload that's larger than 158 bytes and the first and 6 characters are square brackets, and that every 6 byte thing is a square bracket for 155 bytes, which was the exact case here, then, you know, do a warning. But like, it's not just like square brackets and dots. I tried, well, what if I did the square brackets with something else and just like hacks, and I still get an error because their edge case is just looking for the square brackets. So thing with this recipe to really pay attention to is this is legitimate. I'm taking the hacks, I'm deflating it and just reinflating it. That shouldn't be an error, but they put in a stupid edge case. What is this edge case? Well, we have the tools, so let's reproduce it. In this case, we just stored it in InfGen and see what the actual problem is. And it's related to what I was talking about. It is a length too far back kind of an issue. In this case, they had the square bracket, and then they said length of 158, go 5 bytes back to find it. And that's why it repeats that square bracket, and the dots are the nulls, because that's what it's representing, the nulls as its dots. So like I wanted to try to do something like that, but without the square bracket, just to see if it would error out on that, which you know it's not gonna, but I just gotta improve my point here. So in this case, I'm doing X instead of a square bracket, and then I'm doing the same 158.5. I take that, go into CyberChef, and you know, if it really should be erroring out on that error condition, then it would for that too. And just to verify, you know, InfGen, it's showing that we have that 158, or the the 158.5 and then 5.1 too far back, but with the X this time. So when we go to CyberChef, we put that in there, and it's going to work this time. Of course, we're going to put it, after we inflate it, we're going to go back 2 hex just to see the binary of it. And again, nulls. I swear, we'll get to the bottom of where those nulls are coming from. But as an aside, I told the people that maintain CyberChef that that's dumb, remove it. And then they did. All right, so that gave me an idea. Those nulls, I want to build the biggest buffer I could possibly do in one block, which in this case is about 32K. So I wanted to do 32K of too far back. I wanted to see how far back I can peel and if there's anything more interesting than nulls. I mean, long story short, there wasn't, but you know, this is the proof of concept for it. So I crafted that in Deflate, and then I paste this buffer into CyberChef. So from hex, then I'm going to inflate it, and then I'll do 2 hex again as well. Right now it's 32K. At the bottom it's really small, and then when we inflate it, it's like 95,000 something. That's because, you know, with the space of a delimiter and the 2 ASCII nibbles, that's like, it triples what it thinks. But anyway, so yeah, it's just nulls. Still haven't really got to the bottom of that. But before we get to the bottom of that, let's play with it a little bit. We can introduce nulls that kind of are illegitimate in a way, which is interesting. So as a proof of concept, I'm really not going to go into too much measures explaining why I'm going through some of these steps here. Like this first step, I'm only doing it to create a checksum because I'm going to create a gzip file. So it's kind of doesn't seem that sensible. But in this case, I'm using DEFLATE to manually craft the word test, and then I do 4.8 as the pattern. So going back 8, which I don't have, it should be a bunch of nulls, and the checksum is going to match what would be with the nulls. And in this case, I try to use pigs to extract it, which pigs, it's written, I mean, Mark Adler's behind that too. He's also one of the main people behind gzip. Pigs is pretty much like gzip, if I understand this right, except for it's multi-threaded, but it's more modern. And when I gave pigs this test.gz, it says no, this is invalid, which it is. That's what it should do. You shouldn't be able to be extracting this. Gzip version 1.13 and not version 1.13, but I'd say version 13. It's modern enough to be like no. And then I took the hash, the SHA-256, just to show. It starts with 3b, ends with F3. Just this is the file. Just to say, when we go into an older version of Ubuntu that I had. And this is going to be gzip 1.9, which is an older one. We try to extract test there, and we get it. So this is before they were doing this check. So let's get weirder with that. So now I have a file called lol.gz. This is a hex dump of it. We're going to do gzip with it. Same problem. The newer gzip can't handle that. But if we use the older gzip for it, we're going to, it's gzip compressed. There's the hex dump of it. We're going to extract it. No errors. We have our LOL. What is it? It's an elf executable. Okay, let's make it executable. We're going to run it. Well, what? So the cool thing here is you can create a file that can extract something legitimate, but not on newer gzip. I mean, I don't know what to use that for, but I think that's kind of interesting. And just as an aside, how does a browser handle this? So, I made a proof of concept, same kind of thing, test, and then, 10 characters go back 50, end of block. It sort of looks okay so far, but the browser just pukes when it sees that. So the browser, that's what it should do. It shouldn't be handling that like CyberChef. Okay, so to really go into what gzip is doing, debugger time. And I'm not going to, don't have a lot of time to go really crazy with it. I'll give you the short of what's happening. But, when I get into this section where it's actually copying the bytes from the buffer, doing that part of it, you go up all the functions and you get to the mem copy. And for mem copy, it's just length, source, destination. If you look at the source and the destination, so the source is, they both start with 4.3 in hex, and then the source is FFDF. The destination is 7FE3. For those, really long story short, the destination comes before the source. So what's actually happening is it's not going back to find nulls. It's actually, it's coming around to the end and back. So it's like, in a way, this makes total sense, because if it was accessing a buffer and shouldn't have, like maybe the OS would be throwing an error, like that you would be having more problems. So it makes sense that this is why you're not getting an error, but also why you're getting nulls, because it's pre-initialized and there is no data in it. So I was glad to get to the bottom of it, disappointed that it was something so simple, but that's the story for that. Cool. I'm going to check the time real quick here. I think we're doing good, because now we're going to get to the next algorithm, the Huffman codes. A little bit more complicated, but conceptually still not that bad. So in this case, we're using the example phrase of no error to report. I use this phrase because there's repetition in the letters. If it were just ASCII, these are the characters in this table and the binary it would represent. That would be 18 bytes. What if we could say, well, we're only using like 7 characters, including the space. What if we just did 3 bits for each? Of course, we could save there, but that'd be naive, because of course, with real data, we're going to have more than just those 7 characters. But what if we could vary the amount of bits that we use for each one? Like, what if the letter E was really frequent, but the letter Z wasn't? So maybe we can code the letter E with like 2 to 3 bits, and yeah, the Z we might have to use like 9 or 10 bits, but that's okay because we only use it a couple times. That savings is worth it. So like this is an example of what that could look like with just these characters, like a little north of 6 bytes, 49 bits. And this is not just abstract. Again, I really like to get hands-on with this. So in this case, I'll just show like no error to report in CyberChef, and I'm gonna run deflate on it to actually compress it. I'm choosing to use dynamic Huffman coding, so we get that Huffman table and we get our blob there. So now that we have our blob, we can go to InfGen and inspect it and actually look at what that table looks like. That's one of the cool things about InfGen. You can really see all the internals. So, and in this case, color-coded. That's what the table looks like. I'll come back. Did I mess it up?
I'm just checking it.
Go for it.
Just wants to be a little more pointed towards your gob there. Yeah.
All right. So I'm just bringing the table back from InfGen to show this is the same. It's not hypothetical. So it makes sense if we look at the ones that are really short in bits, like the O is 0, 0 and R is 0, 1. If you look at no error to report, there's a lot of O's and a lot of R's. But if you look at the ones that are a lot of bits, 5 bits each, the N and the P have 5 bits each, and really there's only one N and there's only one P in the phrase. So conceptually, that's Huffman tables. Like, yeah, if you want to breathe manually and encode it yourself in binary, like I'm not going to talk about that. Like, we could after, but that does get pretty crazy. But that's conceptually all you got to do. That's kind of the algorithm for doing it. So one of the things is like, well, what about delimiters? The beauty of how it's encoded is it's a binary tree, so there actually is no ambiguity. It's really clever. In the RFC 1951, this is kind of talking about that, but yeah, no time for that. Let's talk about some Huffman ignorance now that we're in here, now that we understand Huffman tables. So what about just filling up the whole table and not using it? Like we make a table for all of our alphabet and then we just end the block. Like what would that look like? This video is a little bit longer. By that I mean like not more than 30 seconds, but I'm using DEFLATE to just max out everything, max out the whole alphabet I'm going to be using and all the bit links for all the characters just to make this table as big as I possibly can. And interestingly enough, the Huffman table itself is encoded with another Huffman table. It's and it's like while DEFLATE is pretty useful to be able to manually create your own Huffman tables, it's still tricky. You kind of still have to understand what you're doing because you can do things like oversubscribing or underutilizing. Like which like I try to make it a little bit easier with the tool that it'll tell you how many codes you have left and all that as you're building it up, but it's still kind of an art. But okay, so now we finally got our buffer. We're gonna go over to CyberChef, and it's a lot of data. That's now it's binary. Let's inflate it up. Nothing. It's funny to me. And to pop the hood, we'll tell InfGen to analyze this. And really, I just want that color-coded bit pattern. So, like I said a long time ago, yellow, that's the Huffman table. There's a lot of Huffman table in this. If we want to look at that and just kind of pick the pieces apart, bit by bit, that purple bit, that's saying it's the last block. So if it was 0, that would mean there's more blocks to follow. We want dynamic mode, means using Huffman tables. We want the max amount of literal length codes, the max amount of distance codes, the max amount of code length codes, which is that's the part of the Huffman table encoded as the Huffman table. And then that's the actual codes that are building up the Huffman table. And this is the Huffman table. And then end of block in blue, and those 3 white 0 bits are the padding. But yeah, you're ending the block before you even use it. So that's how that one works. What about this? This is just another stupid compression trick here. So we have this blob here. I think this is the legitimate one. What we get out of here is the word hacks, H4X. But point is for this, it's a binary blob. What if we took out the conversion of from hex and we have this phrase, 5, carriage return, IR, $, blah, blah, blah. This decodes to hacks as well. But the cool trick with this is that this is not binary, this source input. This compressed data, this compressed blob of data, it's all ASCII printable. That's actually kind of hard to pull off. The way that looks, I'll go into ImpGen and pop the hood on this one. All right, so still lots of Huffman table, but we actually are using some of it. In this case, we have our 4-bit literals, so H, 4, X, and end of block is also a token we got to use. Each of our bit links are 4 bits long, and so the reason I did that is so they're all aligned, because I don't get that many characters to choose from when my Huffman table is only really encoding for 4 different things. But yeah, another stupid compression trick. And we already talked about packing in arbitrary data with the network proof of concept. So now let's just talk about some general ignorance that uses all of those tricks. R.zip. This one's really cool. So r.tar.gz, you extract it, it puts r.tar.gz into a directory called r. You go in there and you extract it and you get the idea. The hash is the same every time. That's some just dark arts right there. Because you are having to do manual crafting manual compression there, and also the author of this being that this is a GZ file and also the .zip that this applies, you have to recursively understand the checksum too. And I read his blog. They brute forced that. Well, what else are you gonna do? That's what that one looks like. R.zip. It's cool. Another little bit of ignorance. For a little while, I was handing out this business card, hacker card. A lot of people thought that this was like just like a PGP key or something like that, but it's not. The idea was I saw a lot of hacker challenges at conferences that were just like decode base 64, you win. It's like, that's kind of dumb. So I wanted to make something not to challenge people, but like I'm big into satire. So this is base 64. There is a clue here for what the next step is going to be. It's hard to see from here, but there's a couple of characters that are light blue. So those characters spell it deflate. So at least you know when you go into CyberChef and do it, you know what the next step is. So let's solve this code in like less than 2 minutes. We'll go into CyberChef. We put that in there from base 64. Obviously, it's binary, so let's do 2 hex. And then in this case, we're going to inflate it. And there's a couple clues here with what we end up. It says 100 or 1024 at the bottom for how many characters we have. Know that this is ASCII hex, so it really means this is 512 bytes. It's clue 1. It ends with 55AA. It's clue 2. The other clue, this is kind of obscure, but if anybody does a lot of reversing and looks at machine code a lot, that 31C0, XOR EAX, EAX, like that just kind of pops out at you. So it's executable. That's third clue. Long story short, that's a boot sector. So let's boot it. We're going to echo this buffer out. We're going to use XXD to make it binary. Call it card.bin. We're going to use Kemu to boot it. And it asks us enter the last 9 LZ distances. It's asking for a password, and it's XOR encoded. So, well, now we got to actually pop the hood, and what are the last 9 LZ distances of the compressed blob there? And there they are. So there's some like recursive stuff or self-referencing stuff going in here. The challenge was harder to create than it is to solve, and I kind of like and prefer that asymmetry. Of course, it's easy to make something that will confuse people. It's easier to do that. But anyway, so the result of that, I'll make it a little bit bigger because the screen. But so this is what you end up with. You enter the password, and it says hacker challenges are pointless. Am I right? So let's talk about forensics. We're kind of getting near the end of this. And then I'll talk about the covert channel stuff right after this. So we'll go through this pretty quick. But there was a tool out there that looked really cool. It's called ZipRec, and it takes the same approach that I ended up taking, except that they also apply some LLM stuff to fill in the gaps, which I thought was really clever, honestly. But my problem with it is the same problem all the other 3 open cases are with this GitHub repo, is you can't compile it. I mean, I felt dumb, but then being that everybody else was not able to do it, I'm like, I'm just going to make my own. So my tool is not as good as this tool, but you can run my tool. So hypothetically, consider a fragment of data. It was the part that was in red. Alignment is the big issue. You can't just paste it into CyberChef and get something sensible. So in this case, we're going to try anyway, and we're just going to delete bytes off the front and see if we get anything. It's like broken buffers. Oh, this looks like words, right? And then we keep on deleting. Oh, no, it's garbage. It's garbage. And so that approach doesn't quite work perfectly. You kind of do need a tool for it, but I just kind of wanted to show what that would look like. So we get back to a demonstration here of toe knife, because scalpel, toe knife, forensics. So we put the data in there, and this kind of allows us to just look at examples, and when we land on the right one, it'll tell us what we have, but it also will give you those linked distance pairs. And then once you land on it, this version just shows you what the table would look like, so you can have a good idea of what you might want to guess. I'm going to give it some guesses for those linked distance pairs, the word for and the ERS, because that seemed right to me, and give it that as hints or clues as opposed to using an LLM. And then I'm able to get the result, which is it even backfills for what the link distance would be before the fragment. So in this case, we end up with ERS and then a bunch of questions and then four is the only of those that has 4 letters in it, is the phrase. If you want to see what the whole thing looks like, that's a screenshot of like the full buffer, not the fragment. So that's what the original sentence would look like. So really, the RFC says that 1951 for in Deflate says you shouldn't really, it's not meant to look at arbitrary data, which makes sense, but that doesn't mean it's impossible. So let's talk about some covert actions. This is Stego territory, and I'm bored of Stego, but like I know it's possible here, so talking about it. What is interesting about this PNG-based Stego, though, is that the bits or the colors aren't going to change at all. That because traditionally, change red a little bit and you can code a bit. No, we're not changing the actual data at all. So, here's all of our PNGs, different file sizes, different hashes. We're going to look at each one of them. That's one, that's one, that's one. They're all the same. The data is identical. So if we look at these kind of one by one, looking at the hex dump and the impgen output of it. In this one, this is stored mode, so not compressed at all. So we see the first 0 is not part of the actual PNG data, but the 25500, that's your red. The 02550, that's your green. The 00255, that's your blue. In this case, we're using dynamic mode, so we do have a Huffman table, but if you look at the literals, again, that first 0 is not the color, so we have a 25500, that's your red. Then we say match 6, there's going to be 6 more bits, or bytes in this case, and then go back 4 to find it. And it kind of like that unevenness is what gets your green and blue. We do the same thing without a Huffman table, so we do fixed mode, and it's the exact same approach there, just a different way of representing the same data. Again, fixed mode, we do it a little bit differently with our linked distance pairs, but the end result is the same data. Same data, same data. Many ways of saying the same thing. So I got to a point where I kind of wanted to automate not just this concept of creating many different arbitrary variations of a file, but also to hide data in the Huffman tables. And I am writing this tool, and it is working pretty well. I haven't released it, and I don't know if I plan to. I could not in good conscience make this tool public without writing the tool that can detect this nonsense. And not just the nonsense of my tool, but all nonsense of Deflate. So this tool I call Deflate Deflector. It detects anomalies in Deflate. The 5 big ones that I do is unnecessary repetition. So let's say we had the phrase OMG hacks, OMG hacks, OMG hacks. If you were to look at some Deflate and you saw those as literals, like no linked distance pairs, but just literals down the line, that's suspicious. You should never see that. If you're compressing with anything legitimate, it is going to make those patterns. So that's suspicious. The tool detects that. But even if you're not splitting the pairs right, or if you're not like crafting the pairs the most efficient way, that's still suspicious. So like, let's say OMG hacks, we could say 6 characters, go back 6 to find them, 6 characters, go back 6 to find them. That would work, that would decode, but that's still suspicious. Your compression tools are not going to make that. What it really would make is 12-6. That's what you'd expect to see. And for proof of concepts like the r.zip and my business card, they both, split pairs ends up in both of those. Empty blocks. Well, we saw that with the me just crafting an empty block to see what would happen. But like, yeah, that's also suspicious. Underutilized blocks, that's definitely the network proof of concept. So I have a Huffman table built up, but I'm not using all the characters from it. I built the Huffman table to put the data in, but not to use it for the actual message. And if that wasn't enough, what if you were clever enough to make your Huffman table to put all of your encoded data in, that your secret data, but you were clever enough to actually use every single symbol in that table to try to thwart this even? Well, statistics are still going to catch up with you. So it has this heuristic as well. So even if I used all of them, it would say, well, the bit length in the Huffman table for the letter Z, it's a little bit long, yet you use the letter Z a lot in your actual payload. That doesn't match statistically. So it does that analysis as well. So with this deflate defector tool, there's not a lot of wiggle room to do something sketchy. Pretty much any of the examples, any of the ignorance that I talked about here, this tool would pick up on all that, and other things like r.zip. I didn't write that, but this tool would definitely pick up on all the ignorance in there. So what's next? Honestly, I kind of wanted to do all this before this talk, but life gets busy. These are things I still want to do. This deflate stuff is something I've been kind of obsessing about for like the last 7 years. I just keep on putting it down, like, yeah, there's nothing useful, and then I'm like, oh, yeah. But so this is kind of a passion project. I do kind of vapor some of the stuff I do, but this one I'm still interested in. So one of the first things I wanted to do is spider for anomalies, like just go out there on the internet and not just to help debug my tool and make sure it's better, but I don't want to give the impression that I even think that threat actors are using this as a way to, there's so many other ways to do it. And I mean, of course, I didn't find any evidence of it, but it'd be cool to find weird stuff out there. If there were people using it because there's no evidence of it, it's those kind of people using it. And one of my friends, Lambda Calculus, he's been doing a lot of stuff with DPRK, the North Red Star OS. Like they definitely do some sketchy stuff, and it's been on my mind, which is why I put more energy in the deflate defector as opposed to the deflate tool, and also kind of probably why I called it deflate defector. But yeah, so it'd be really interesting to find anomalies out there in the wild. Not to say that they're going to be malicious, but if I do find an anomaly, it's probably going to be at least interesting. And if this is going somewhere, it'd be cool to write a web service where people could upload a file and get the result back. I guess the use case for that is, maybe it's somebody that doesn't want to download my script off of GitHub and maybe not technical enough. That's fine. So, make something easy for it. But I do want to take considerations with this because, I mean, as far as privacy goes and all those kind of things. And then browser plugin, one of my other friends, he was talking about, first we were landing on the idea of, there's HTTP has deflate, so we can kind of sniff that coming through as a plugin. But at a browser level, it's to the best of what we were finding, it doesn't really see it at that layer of abstraction. So then I guess maybe you'd have to do something like burp and kind of get it at that level. But if the whole point is usability, well, then having somebody set up burp and then use a custom script, that doesn't work. But another thing we're thinking that might be possible is just the cached content, so that the PNGs and that kind of stuff. And by the way, that guy is the one in the black hat over there, calling him out, putting the pressure. He didn't want me to. But these are the three things that I have looking at going forward. Beyond that, I'm just going back to this like I've been throughout the whole talk, just to show these are the tools involved. And cannibalizing it as the questions last slide. So that's all the content I have. And I can do Q&A.
What questions do we have? One back here.
Okay, is there a mic or just?
You can run with it if you want.
Okay, cool.
Or we can repeat questions up here. Or if you want to come up to the mic, you can come up to the mic as well. Either option. No, well, this was the mic here, but maybe it's been kind of.
Or you can just use my mic, right?
We're making this complicated.
Yeah.
Ask the question.
Yes, yeah. What's
thank you. Actually, did my graduate thesis on Deflate,
Whoa.
and you just hit a bunch of awesome things. So, good job. If you want interesting data sources, have you looked at the hardware compression devices that will do Deflate? Because they have some interesting characteristics.
No, maybe we should talk after, because one thing you know how I was talking about with Gzip and other things, I was kind of expecting maybe there's a heartbleed for, well, there wasn't, not because of Deflate, it's just implementation specific. That's just how Gzip handles that illegal distance. But if somebody else is reinventing the wheel, they might do it differently. So I am kind of interested.
There's hardware, and then I have not investigated them deeply, but there's a vast number of re-implementations of Deflate, especially for embedded hardware, which could be interesting targets.
Right, especially because they're going to probably be doing some savings on code size. They might be doing some tricks that, yeah, I'm interested. I'm absolutely interested. I really mean it, like maybe after this, like I can get some notes from you.
Definitely.
Cool.
Any more questions? Right here.
Just one excellent talk. This is really cool and very educational. I'm curious, so you start off with the LZ77 compression algorithm kind of going through. I'm curious if you've seen or if you've played around with the LZ78 or LZW. That I think LZ78 is it builds its dictionary and then it builds a secondary dictionary on top of it and references the second dictionary for repeated instances. And then LZW pre-initializes the dictionary. And I'm wondering if that might be like for Deflate, that might throw some interesting curveballs for it.
Yeah, maybe I haven't played with those. No, yeah.
The question was on LZW.
Yeah, if I played with LZW or LZ78, yeah, no, I haven't played with those.
Gotcha. Okay.
Any more questions?
Cool. Well, for the people that accidentally came in here and weren't interested in compression, we can get 10 minutes back. Thank you.